you. Hello, everybody. My name is Fartash from SafetySpect. This is my first opportunity to present our company to space agriculture folks. I would like to discuss a little bit about our capability related to the agriculture and more specifically for the space agriculture. So that's why here I'm talking about the spectroscopy and imaging systems that we are building for space agriculture applications. So who we are a Grand Forks-based biotech agtech company. Our focus is multimode optical sensing and artificial intelligence for multiple applications, from agriculture, healthcare, safety and security, military, and so forth. And we are very focused on edge computing capability. What is edge computing? Is that all these AI machine learning algorithms happening in the system. So there's no upload and download of the data. And we are positioning ourselves as a dual use company that's serving bringing solutions for unmet need in both government and commercial space. So our strategic partner in academia is University of North Dakota. Actually, we have a presence in the bioinnovation zone led by Kuyar, and also we have two strategic partners at USDA ARS led by Dr. Moon Kim, who is here, and also US Army DEFCON. And part of this work has been partially funded and supported by these agencies. So again, my background is optical systems and AI, so I would like to educate you about the plant stress. You know that better than me. So we have bionic stress, abiotic stress, and usually the traditional method to monitor and detect them is to send them to the lab, or basically visual inspection, which is very subjective. So what we are trying to do is building the optical spectroscopy and sensing systems for early detection. So we will monitor how the plant behave during the water stress, nutrition stress, or pathogens, and with the AI, we are trying to predict, create a model to actually minimize the damage to the plant, which is going to be very critical for the NASA missions, as previous speakers were talking about. And spectroscopy or optical sensing has a very rich information about plant and tissues and so forth. And these are like examples of things that you can extract from the optical spectroscopy, from chlorophyll, water content, pigment, photosynthetics, and so forth. And but the issue is that each of these, we call it markers, requires different modes of spectroscopy or different modes of optical detection. And how we are trying to address this issue to cover as much markers as possible, we are bringing different modes of spectroscopy together to have a wide range of markers detection. So this is our first platform that I would like to talk to you. We call it CAT, QAT. It's coming from Quality, Adulteration, and Traceability. So this project launched about 4 years ago. We got established our CRADA, Cooperative Research and Development Agreement with USDA ARS, and we start building the spectral library for seafood issue. As you may know, the seafood fraud is huge in United States. So we gather these optical spectroscopy data to see if we can detect different species of the fish and detect the fish fraud. We actually targeted the red snapper. We bought 12 red snapper from online sources, and we DNA tagged them. And guess how many of them was red snapper? 2. So that would give us a very strong motivation. After that, we got the NOAA SBIR phase 1, phase 2, and we built this technology. And the picture here shows basically what is in our CAD technology handheld system. So this system compromising fluorescence spectroscopy with 2 excitation wavelength, as well as reflectance invisible and NIR spectroscopy, all in one handheld system. And we are leveraging right now the advances on the LEDs, sensors, computations that become more and more miniaturized into the handheld system. And we are expanding this technology in multiple applications. We started from fish, seafood, species identification. We realized that our device can also detect how many times that fish is frozen and thawed. Is that farm raised or wild caught? And also, when we go from fresh to rotten, we can actually track the changes on the spectral signature. We move it from basically fish to red meat. We have a project that is going to be a very big project for North Dakota. It's not finished, but this is going to be a very big news for North Dakota on a skin analysis for senior population. But also, we are very interested in agricultural application and use this device to monitor the plant health and so forth. Again, this is the original, basically, use of our CAD technology for adulteration, for quality, and so forth, mostly targeting the Food Modernization Act. Right now, we have an active pilot study with University of North Dakota. One of the PhD students is actually growing this plant, and we are testing it with our handheld system. And this is like a just first week teaser of the results that we can get, the control versus water stressed plant. And you will see that how this spectral signature in fluorescence, when we excited in UVA with the blue, reflectance in visible and reflectance in NIR can change. So this technology, we started developing the minimum viable product at 2022. This year we released the handheld prototype, and we are anticipating to release the commercial sales with edge computing capability in 2026. The second platform that I would like to talk about, we call it Moonlight, in recognition of Dr. Moon Kim. And this technology is basically an imaging version of the CAD technology. So it's a line scanner, hyperspectral imaging system with the LEDs that facilitate both fluorescence hyperspectral imaging and reflectance hyperspectral imaging. And we are basically, with that, we can not only look at both the spectral signature, but also we can understand the spatial distribution of the plant. We are also adding thermal imaging and LiDAR. LiDAR will give you the size, the height of the plant, the 3D structure of the plant. So this is going to be very interesting project because you're dealing with a lot of dimensional data from a fluorescence perspective, reflectance, spectral data, image data, thermal, and LiDAR. And that's why we need the edge computing AI to analyze this multi-mode data for plant analysis. So this project is in collaboration with USDA ARS at Beltsville, Maryland. And we are right now building this moonlight system for Kennedy Space Center. So they have a growth chamber there. The picture that you see here is an older version of Moonlight. So we are doing a series of improvement on the thermal stability, illumination uniformity, and so forth. And these are like examples of the data we took at the USDA lab. So that's the summary of my talk, and I would like to discuss with you if there's any collaboration, any opportunity that we can bring this technology to your farm, to your lab. I would be happy to discuss that.